We're going to continue our work with functions, and now we're going to be analyzing the graphs of functions. So let's start with an example. So here's a function, and I want to find the domain and the range of this function f of x. As you can see, this is a piecewise function. And so to find the domain, we want to know what x values give us outputs for our function. So what I have over on the left here is what I call my domain finder. And as I slide that across the screen, it's a vertical line representing all the different x values. So as I slide this across the screen, when it hits my graph, it beeps. Beep, 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 beep. I know that seems silly, but it gives you the right visual for that. So when did it beep and when did it not beep? So it beeped when we finally got to this x value, which is -4. And then it kept beeping. And even at x equals 1, the open circle at the bottom, it wouldn't beep. But because we have a closed circle at the point 1, 1, it still beeps. And then it's still beeping and still beeping. And then it finally stops beeping at x equals 4. And then continues to beep again, and the arrow says forever. So in terms of writing down what's the domain of this function, it goes from -4 to +4. We include the -4, but we're not including the +4, union with the interval from 4 to infinity. So basically it's going from -4 to infinity, except at x equals 4. All right, now let's go back and look at what about the range? Well, I happen to have a range finder here as well, and this is horizontal, and I slide it up across the screen from the bottom, and whenever it hits the graph, it's going to beep. And when it beeps, those are values that are in the range, or y values. So it's not going to beep, and all of a sudden, still there, it's an open circle, so it's not beeping. Now it's going to start beeping. Keeps beeping, keeps beeping, keeps beeping. Here it's beeping because there's several spots where it's hitting. Keeps beeping, and then after there it stops. So what y values was it beeping for? Well, not at -2, but then greater than -2, and 0 and 1 and 1.5 and 2 and 2.1 and 2.578, keeps going, still hitting the graph. And then finally, after there it stops, which would be at y equals 6. So that's the last value that it takes on. So it goes from -2, not including the -2, all the way up to y equals 6, and we want to include the 6. And so that's going to be our range. And so you can see it's pretty easy to tell if you have a graph. So there's your domain and there's your range. Now, what if you don't have a graph? What if you just have an equation? Find the domain and range of g of x equals the square root of x minus 3 plus 2. Well, if you remember anything about what a square root graph looks like, square root of x, I'll just do that by hand here quickly. So here's your square root of x graph. Now, what happens with the -3 inside there with the x? Well, that shifts it 3 in the opposite direction. So 3 to the right. So it's going to move 3 to the right, and then the +2 outside of it is going to shift it up 2. And so there's our graph. So it had shifted 3 to the right and 2 up. So now we know that it starts there and goes on. So if I want to write the domain, it's going to go from 3 to infinity, and we include the 3, and notice we can plug 3 in for x there, and we get a valid expression. We get the square root of 0, which is 0, plus 2 is 2. Oops. Let's erase that. Put that back on there. Okay, what about the range? So the range are all the possible y values. So that's, if you think of that, let me draw that in here. Think of that range finder again. When does it start hitting the graph? It starts hitting it right there at y equal 2. And then even though this curve levels up, it doesn't completely level up. It continues to go a little bit up forever and ever and ever. So it keeps going all the way to infinity. So for our range, it's going from 2 to infinity, and we're including the 2. All right, so we have some definitions that we need to work through here, and it's important that you understand exactly what it's saying. In mathematics, when you read a definition, quite often you have to read it several times, because every word in there is important, and if it wasn't, it wouldn't be in there. So a set of points in a coordinate plane is the graph of y as a function of x. Now, if I said is x a function of y, that's a completely different question. Y is a function of x if and only if no vertical line intersects the graph at more than one point. And we've talked about what is a function and what is not a function. And if you had a bunch of ordered pairs, you're looking to make sure that the x value doesn't get assigned to more than one y value. Well, if you take those points and plot them, if one x value was assigned to more than one y value, those points would be plotted on top of each other, and therefore a vertical line would hit both of the points. So that's what we call passing the vertical line test. So if any vertical line you draw only hits the graph in at most one spot, then it's a function. Some terminology here, the zeros of a function, those are the x values for which f of x equals 0. These are also called the roots of the function and the x-intercepts of the function. So those three terms in blue that are underlined, they all refer to the same thing. The zeros, the roots, or the x-intercepts of a function. And so the y value is 0 for all those points. When is a function increasing? A function's increasing on an interval. So we talk about it only increasing on an interval, not at a specific point. When we get into calculus, we can talk about increasing at a point. For any x sub 1 and x sub 2 in the interval where x sub 1 is less than x sub 2. So that means on a graph, the x sub 1 is to the left of x sub 2 value. If that's true, that implies that the y value, or the output at x sub 1, is going to be less than or lower than the y value for x sub 2. And likewise, almost the exact same definition, a function is decreasing on an interval if for any x sub 1 and x sub 2 in that same interval, x sub 1 less than x sub 2, this time it implies that the output for the left point is going to be greater than the output for the right point. So in other words, it'll be higher up on your graph than the point to the right of it. And if that's true, then it's decreasing for every point on that interval. And then finally, we could have a constant function, and that's where the outputs are the same. So the y values are the same for different x values. And that's just a horizontal line or part of a line on a graph. So let's look at an example here and figure out where exactly is this function increasing and decreasing or constant. So with some calculus, this would be really easy to analyze, but we haven't gotten there yet. So what we're just going to do is look at the graph. So let's take our graphing calculator and let's go to y equal. And as you see, I already have that put in y1, and I'm going to graph at the standard window, so zoom 6. And there it is. If we're following this graph, starting from the left, you can see that we're going to be going up, which means it's increasing, until we get to that local high point, which occurs at x equals -2. And then it looks like we'd be traveling down the graph, until we get to the low point where x is equal to 0, and then it starts to go up again. Now I want to show you how you can verify that, because we just don't want to eyeball it. So I'm going to press the second and the trace key, which is the calculate menu, and I want to calculate number 4, a local maximum. We'll define that in a minute. And then it says, okay, give me a left bound. So I need to hit the left arrow key and go to the left of that high point. And that's fine, I'll press enter. And then it says, okay, give me a right bound. So that means go past the high point to the right of it. Doesn't matter how far you go past it, so that's fine. I'll press enter again. And now notice, it's just going to look in between those two x values. In that interval, and it says, okay, give me a guess at where the maximum is. I'm not even going to waste time with that. I'm just going to press enter. And there it tells you the maximum is at x equals negative 2 point, and notice a bunch of zeros and then a 1. So you have to understand that the calculator is doing an approximation method to figure this out. So when you see an answer like that, you can rest assured it's probably going to be just x equals negative 2. And then the output would be 3. So that point is negative 2 comma 3. We could verify that by plugging in negative 2 for the x's in our function and see if it evaluates to 3, and it actually does. Okay, so our function is increasing from negative infinity to negative 2, and then it's decreasing from negative 2 to 0, and then it's going to increase again from 0 to infinity. So let me show you how to calculate that minimum value just to verify. Second trace again. This time I'm going to choose number 3, minimum. And now I'm going to move closer to that. That should be good. Press enter. Give me a right bound, so go past it a little bit. Press enter. Give me a guess, I'll just press enter. And it shows an interesting number. It says the y is equal to negative 1, but the x is equal to 1.858e negative 6. Well, that's the calculator's way of scientific notation, saying 1.858 times 10 to the negative 6th power. So that means 0.000001858, which is really close to 0. So when you see an answer like that, you shouldn't write that down. You should say it's 0. So that minimum point is at 0, negative 1. And once again, we could plug those values in for x and y in our function to verify that. Okay, so now we're ready to write where this is increasing or decreasing. So the function is increasing from negative infinity to negative 2, and I'm not going to include the endpoint, and then union with 0 to infinity. And then the function is decreasing between negative 2 and 0. So negative 2 comma 0. And notice, because we're using negative 2 in both the increasing interval and the decreasing interval, we're not going to consider it as being part of one and not the other. So we're just going to use parentheses on everything for increasing and decreasing. All right, now I talked about maximums and minimums. A function value f of a, now this is the output value, is called a relative maximum of f when there exists in an interval x sub 1, y sub 1 that contains an a such that x sub 1 less than x sub 2 implies that f of a is greater than or equal to f of x. It's probably more complicated, and don't put too much time into the very detailed definition of this. But basically I showed you from the graph where the relative maximum was, and that was at x equals negative 2, and the relative minimum was at x equals 0. Basically it means over an interval, there's no other output that's higher than the relative maximum, and over another interval, there's no point that's lower than that relative minimum. All right, so what if we actually have to find relative maxes and mins? Well, I've showed you on the calculator how to do that. So if you want, it might be a good idea to hit pause, and then you can try it on your own, see what you come up with, and then check it with the answer here. So let's go back to my calculator. And this is one of the tricks. Now, I don't want to graph that x cubed plus 3x squared minus 1 anymore. I could hit clear, but if maybe I needed that later, I'd have to type it in again. But if I move the arrow over the equal sign and press enter, and then move away from that, you'll notice the equal sign is not highlighted anymore. That means it's not going to recognize y1 when you try and graph. On the other hand, y2, which didn't graph before, because the equal sign was unhighlighted, now I'll move the cursor over there and press enter. Now it is highlighted. So now when I hit graph, it's going to want to graph that second equation in y2. Now in the standard window, we're not seeing quite enough. So there's a few options with zoom. You can do a zoom fit. I like to actually consider what's going on here. it looked like my x values were fine, but my y values I needed to increase a lot. So I'll go from negative 30 to 30 in the y direction, and I'll change my scale to be by 5s. That was enough for the maximum, but not quite enough for the minimum. So I'm going to change my minimum to be, how about negative 35? There we go. All right, so we have one relative maximum. You can see that occurs, looks like somewhere around negative 2 or 3. And then we have one relative minimum, which looks like around positive 3. So I'm going to press second trace, calculate number 4, a maximum. Give me a left bound, so I'll move the cursor to the left of it. Enter. It wants a right bound, so I'll move it past the high point. Enter. Give me a guess, just press enter. And notice it's negative 2.499998. So we can probably guess it's negative 2.5. And then the output is 23.95. So, once again, I can't do the screen capture, so I'll leave that alone. So, negative 2.5, 23, I'll round it, 23.96. 23.96. And that's a relative maximum. Okay, now let's find relative minimum. Let's go back to our calculator. And once again, we'll press second trace to calculate menu. This time I'm going to do number 3, minimum. And now I could hit the right arrow to get it all the way down there, but I'm just going to punch in 2. So it jumps right to there. And then I'm going to punch in 4, and then I'm just going to press enter for the guess. So this time it looks like x is probably positive 3, 2.9999977. So x equals 3 and y equals negative 31.5. X is 3, y is negative 31.5. And so that's how you find your relative max and relative min using your calculator. All right. A couple more quick things. When is a function even? A function is referred to as even if f of the opposite of x gives you the same value as f of x. So it's easiest if I show you an example. So what if I have f of x equals x to the 4th minus 3x squared? Well, what I want to check is what if I plug in the opposite of x for every x? So that's negative x to the 4th minus 3 times negative x squared. Well, because these are even powers, negative x to the 4th, negative times a negative times a negative times a negative is a positive, so that's just going to simplify to x to the 4th. And then same with negative x to the 2nd power, negative x times negative x, that's a positive x squared. Notice this is exactly the same as what f of x was. So f of the opposite of x equals f of x. And so we know this is even. On the other hand, a function is odd if f of negative x is equal to the opposite of the original f of x. So I have an example for this one. So let's evaluate f of negative x. So I'm going to plug in a negative x wherever I see x. And using parentheses is always a good idea when you're plugging in values or expressions. Now, negative x to the 3rd power, that's a negative x times negative x times negative x. Negative times a negative is a positive, times another negative is a negative. So this is really the same as negative 4x to the 3rd. And then minus a negative x is like a plus x. So now look at the original function. The opposite of that original function, if I factor out a negative from what I have, this is exactly the opposite of what I started with. And so this is an odd function. Now it's important to understand that not every function is either even or odd. It could be neither. So it depends on how it works when you evaluate it. The other important point to remember, which is helpful, when a function's even, it's symmetric with respect to the y-axis. So for example, y equal x squared is an even function. And that's because it's symmetric about the y-axis. If you fold this graph on the y-axis, the function goes right onto itself. On the other hand, if you want an odd graph, it's not symmetric about the x-axis, which is what some people guess. Let's go with green. Then, for example, y equal x cubed is an odd function because it's symmetric with respect to the origin. By the way, WRT, with respect to. And what that means is that if you take, let's say, this part of the graph, reflect it over the x-axis and then over the y-axis, it goes right onto itself. And that's what it means symmetric about the origin. And in this case it does. So y equal x cubed is an odd function. And that's easy to remember because 3 is an odd number. And y equal x squared is an even function. And once again, 2 is an even number, so that's easy to remember. Okay, one last thing. The greatest integer function you should have come across at least briefly. And what that does is it takes each input and it outputs the, let me underline this, the greatest integer that's less than or equal to the input. What do I mean by that? Well, first of all, here's the notation. Notice it's not just that. That would be absolute value. But when it has these notches on there, and some textbooks will actually have like almost a double line when they write it. So if you see that, it's referring to the greatest integer function. So for example, if I said, for this function, what's f of 7.8? The answer is 7. And here's the way that I think is easiest to remember. If I have a number line, and that's 0, and I plot just integers, so here's 7, let's say, and here's 8. If I ask you what's the greatest integer of 7.8, which is right here, what's the closest integer to the left of that point? And that would be 7. And so that's the answer. Let me look at a couple other examples just to make sure you got the hang of this. What would f of 2.1 be? Well, if we plotted 2 on our number line, and let's do it in red. So there's 2.1, and 2 would be here, let's say, and 3 is here. The first integer to the left of that point would be 2. So the answer there is 2. What about f of 5? Well, that's actually right on 5, so it's closest to 5. How about f of negative 4.2? And this is the one that always gets people. So here's negative 4. Here's negative 5. Negative 4.2 would be right there. Let's change that to a different color so you don't mix these up. Okay, so which integer is closest to the left of that point? And you can see that's going to be negative 5. And so what a lot of people do is they think, oh, this is just like rounding the number. So when we had 2.1, we rounded it down to 2. 5 just rounds to 5. Negative 4.2 should round to negative 4. No, you've got to think of it this way visually. What's the first integer to the left of it, which is negative 5? And then the last one, 2/3, well, that's between 0 and 1, so the integer to the left of that would be 0.